Hello everyone! Today's our new topic. It's about nature. So in this lesson we're going to talk about the nature of the light reflection and the light refraction. Our objective at the end of the lesson, you'll be able to define the nature of the light, describe the laws of light reflection and the light refraction. Then you'll be able to explain total internal reflection and the Snell's law. As we discussed it in the previous lesson, light, this is example of the electromagnetic radiation, like a radio, microwave, infrared, or other types of electromagnetic wave. So, light is an example of electromagnetic wave. And you know, electromagnetic wave, this is a result of mutual reproduction of the electric and the magnetic fields. So by changing the electric field produces a magnetic field, and the mutual reproduction can carry to oscillate the light propagation. Okay. If we observe this electromagnetic spectrum, the visible light, it just consists a tiny part of this electromagnetic spectrum. So from 700 nanometer up to 400 nanometer, it's a visible light that we can sense by our eyes, guys. So this tiny part of the wavelengths that are visible, that we can see with our eyes. So let's move on. Next, introduction to the light. Actually, we can see the light by the two ways. The first is directly from the light source. For example, from the sun, from the light lamp, or from television, or from the stars. And you need to know that we can see, you see from this figure, only the small part of the light that we can see. Other part of the light, for example, travel in all directions. Second way, we can see the light by the reflection of the light from some objects. For example, this is an incident light toward to the object and the reflected back, for example. So we can see this reflected light, and by this reflection of the light we can visualize other objects. Again, we can receive, so our eyes receives only a small part of the reflected light. Next, basic properties of the light, that light can travel in a straight lines. So this lines, or this propagation, is called a rectilinear propagation. And also the light rays obey the laws of geometry. By using the straight lines or the right triangle or similar triangles, we can solve the many problems. Then the speed of the light in a given medium. For example, it's 3 × 10⁸ meters per second in a vacuum, or rather we can consider also in a air. In a water, it's a 2.26 × 10⁸ meters per second. For example, here is given one example. If the meter stick casts a shadow is 1.5 meter, for example, this is 1.5 meter shadow, and the long tree shadow is 18 meter long. How tall is this tree? So we can solve using the similar triangles. You see here we get similar triangles with 1.5 meter to 1 meter and 18 meter to x meter of this height of this tree. So involving the right triangles, we can solve by this ratio. You know, one opposite over adjacent. Also here it's opposite over adjacent, gives the same angle. Using this, we can find the height of this tree. It is equal to 12 meters. Next, light reflection. There are two types of reflection, guys: specular and diffuse reflection. You know, when the light is incident to the surface is reflected back. For example, here, when the light is incident to the smooth, flat surface, it's reflected with the same parallel rays. So this reflected angle is measurable. For example, if you consider this is a dashed line which is perpendicular to this line, is called a normal line here, and this ray is called an incident ray, and the angle between the normal line and the incident ray is called the incident angle. Angle between the normal line and the reflected ray is called the angle of reflection. By the law of reflection, incident angle is equal to the angle of reflection. Next, diffuse reflection, guys. So diffuse reflection occurs when the light rays incident to the not regular diffuse rough surfaces. So in diffuse reflection also obeys the law of reflection. It means that angle of incidence is equal to angle of reflection, but reflected angles are not like measurable, so it's difficult to measure. Why? Because incident rays are parallel, which is traveling toward to the surface, but the reflected rays are not parallel, so it's more difficult because it's scattered in all directions, guys. So this law, this phenomenon, called reflection. For example, look here, incident angle is equal to reflected angle by the law of reflection. Let's consider, let's examine some examples. For example, first example, what is the angle of the reflection for the light ray in the diagram below? For example, if the angle between the surface and the incident ray is 20 degrees, we can consider that by drawing the normal line, we can find the incident angle. You see, it is subtracted from the 90 degree. So incident angle is 70 degree. If its incident angle is 70 degree, refracted angle also 70 degree. Or this problem, for example, if total angle is 150 degree, what is the angle between the reflected ray and the mirror surface? So here we need to divide by 2 because incident angle equal to reflected angle. It's 75 and this angle is 15 degree. Next example, how images are formed during the specular reflection. For example, when you are traveling in a beach, for example, in a beach of the river, you can observe, for example, in a shiny day, you can observe a side view of this river. For example, if on a beach is here is a trees, you can see the image on the surface of the water. So surface of the water, it works as a mirror. For example, this is here occurs a specular reflection. So we can see the image of the object in a water surface, like in a mirror, by drawing a dashed line. Why? Because these reflected rays not crosses each other. This object, for example, letter A, created behind the mirror by drawing the imaginary, like virtual lines. So to get an image, all the lines must cross each other. So when we draw a dashed lines, in this point, all the lines are crossed each other. So here formed an image. So this image is virtual image. Why? Because we formed behind the mirror, and also it formed by the virtual lines. Next phenomenon interesting physics phenomenon, guys, it's a refraction. For example, in everyday life, we can face examples of the refraction. For example, when we put something into the water, cup of the, for example, you see water in a glass cup. If you put this pencil, you see, you can see this kind of like figure. Why? Or, for example, in a hot summer day, we can observe a mirage. So mirage, guys, is a naturally occurring phenomenon, you see, caused by the refraction. Or, for example, this, what is it? This arrow, when you observe through the glass of water, for example, this arrow is reversed back. So all of these, guys, are examples of the refraction. So refraction, this is bending of the light when it travels through the medium, guys. For example, here, here or here, you see, this here is a fish, but for your eyes, it will be, it seems like that it's located in this position. Actually, this is a apparent position. This is a real position of this fish. So in all examples here, guys, the light wave traveled from the image, for example, from here or from the pencil, and then into the water. For example, in this example, into the water, crossing the glass cap, and finally traveled out of the glass through the air, and then into the through the air and reached to our eyes. Here, water acts, you see, as a magnifying glass. For example, when you do this simple experiment at home, this pencil gets bigger. It's like magnified. Yeah. And then it looks like a, for example, here reversed or just magnified. This is depends on the light which is traveling through this medium. Here, this is a light, it's traveling through this medium and reversed by the focal point. That means the light on the left direction, for example, is now changed to the right direction. Why? Because when the light rays goes beyond this focal point, guys, means the point which all the light rays is gathered in one point through the medium, then image looks like reversed because of the light is reversed. Okay, let's move on. So refraction, guys. Refraction, this is a bending of the light when it moves from one medium to another medium. So refraction occurs when the light travels from one medium into another medium. For example, from air into the water. The light, guys, slows down when it enters to the more dense medium. For example, air is less dense than the glass. So this light, which is incident, it bended when it enters to the glass. Why? Because it is slows down. By the universal wave equation, frequency remains constant, but wavelength is decreased. So far, the speed of the light also decreases. And when it re-enters through the glass, it again speeds up. So here occurs a phenomenon which is called a refraction, guys. So light is partially reflected and partially refracted when it travels through the medium. Okay, so here we can understand by the ratio of the speed of the light. As we said, that speed of the light is decreased when it enters from less medium to more like high denser. You see, as the light goes into more dense medium, it bends toward to this normal line. So refracted angle is less than incident angle. When it travels from more denser to less denser, it is bent away from the normal line. Then ability of the medium to slow light down is called refractive index. So what is it, a refractive index, guys? Refractive index, this is a medium gives an indication of the light, like light bending ability to the medium, how it bended, more or less. So we can find by the ratio of the speed, C is the speed of the light in a vacuum, to the V is the speed of the light in a medium. For example, here is given a table for index of refraction. In a water is 1.33. You see, in a vacuum, 3 × 10⁸ meters per second. V in a water is 2.26, 10⁸ meters per second. If you divide, you get a 1.33. For example, diamond 2.42. So when the light travels from air into the diamond, it bends more because index of refraction is bigger. So let's move on. And the Snell's law. What does it mean? Snell's law. Snell's law indicates that the ratio of the sine theta of incident angle to the sine theta of the refracted angle gives you a constant number. For example, when we use this simulation, you see, when I increase the incident angle, also changes you see, refracted angle. So ratio of the sine theta of incident angle to the refracted angle remains constant, gives you a constant number. And also this constant number we can get by the ratio of the index of refraction. N2 over N1 also gives the same number by the angles. Refraction, total internal reflection. In previous slide I said that when the light traveled from more dense to less dense medium, it bended away from the normal line. For example, in this case, when we increase this incident angle, for example from water, also it is bended away from the normal. So this angle also increases. So far as the angle increases, refracted ray, you see, starts to approach to the what? To this boundary. So until we get to point, there is no refraction. So after that, after this angle, it is not refracted, reflected back. So this phenomenon is called total internal reflection. And this angle, guys, which is after this angle, light not refracted, reflected back, call it a critical angle, guys. When you add to the reflected angle, here it gives you a 90 degree. So total internal reflection examples. For example, here a diamond. You know, guys, diamond sparks in all directions, because here when the light is incident through the diamond, here occurs a total internal reflection. So light will won't refract, reflect inside by the what? By the surface of these diamonds. Also, this total internal reflection widely used nowadays in a transmission, like in a data transmission. For example, nowadays in all houses procured by the what? By the fiber optic cables. So these fiber optic cables, our internet, guys, internet, you know, guys, nowadays our speed is very high because of the what? Because of using these technology. So in this technology here, the data sends with the pulses with an total internal reflection. So you see guys, uses the pulse of the light to carry the information sensed by the with a critical angle, and this data not refracted are just reflected back and can travel very faster. So you see it can travel 100 times faster than the metal cable. Then how to find the critical angle, guys? Okay, here is given an example. You know, by the Snell's law, we will consider that one of the angle as a critical angle. So next angle, this is, for example, this here, and 2 sine critical equal to and 1 sine 90 degree. Why 90 degree? Because here guys, when the light traveled from one medium, okay, let me show here. Look here, when the light traveled, this angle will be a critical angle, because so this is a critical angle when the refracted ray is roughly equal to 90 degree. What is it 90 degree? 90 degree here guys. So we can consider that second angle of reflection is equal to 90 degree, and by the equation of the Snell's law we can find this critical angle. Okay, next, dispersion of the light. First, basic 5 colors can be observed by experimentally by Isaac Newton, guys. He did a lot of works in a gravity. He also figured out some key points of the optics, guys. So he discovered that light can white light split it off into different colors when it traveled through the, for example, this kind of prism, guys. So splitting off into different colors is called a dispersion of the light. Why here we'll get a different color when the white light travels through the prism? Because when the light travels through the prism, it bended, like it refracted, and changed wavelengths, changed the speed. Speed means which reduce it in a screen different wavelengths of the white light. For example, here is given a range of the wavelengths of the light. For example, violet is a 400 from 400 to 450 nanometers, guys. So by that our lesson is finished. Thank you.